Okay, I'm gonna go ahead and we'll get things started here. So welcome. I'm Dr. Wes Hines. I'm the Nuclear Engineering Department Head here at the University of Tennessee. This is our weekly Colloquium series. And today we're very excited to have Dr. David Poston, who's a senior research designer at Los Alamos National Laboratory. He's been responsible for the design and the development of nuclear fission reactors for civilian, NASA, and defense applications in space. Dr. Poston is the reactor designer for NASA's Kilopower project, including the Duff and KRUSTY reactor experiments. He has 25 years of experience in space reactors and has been primarily focused on near-term concepts for solar system exploration, including designs for missions to the Moon, Mars, Jupiter, and Neptune. In addition, Dr. Poston has developed several nuclear thermal rocket design concepts for NASA over the past several years. Prior to his experience at Los Alamos, he worked at GE Nuclear Energy for 4 years on advanced reactor designs. He received his Bachelor of Science in Mechanical Engineering from the University of Michigan, a Master of Science in Mechanical Engineering from Stanford, a Master of Science in Nuclear Engineering from the University of California, Berkeley, and a PhD in Nuclear Engineering from the University of Michigan. Welcome, Dr. Poston.
Thanks. Yeah, I went back to Michigan because that was the best school out of the three. So that's me, and then Pat McClure standing in the middle there. He really was instrumental in getting us through the safety and approvals process, and understanding how that whole world works. And then Mark Gibson on the right is a fantastic mechanical engineer and a hands-on guy that just did a great job from NASA. And then there were a lot of other people involved, but I really want to talk about making nuclear real, right? Instead of, it's the last 30 years has been horrible to be a nuclear engineer if you care about reactors, because we haven't done anything real in reactors. So hopefully you students are going to have better luck than us. And our goal here was to actually get something actually moving and do something real. There's a million projects right now, and you see it all the time, to build reactors. People are getting money left and right. But until we see one built, I would be skeptical. But and it's 40 plus years of reactor technicians is what led us to this project. Not just in fission reactors, which we spent, space reactors, we spent several billions with no progress, but the DOE has spent, since the DOE was formed, it hasn't started and completed a reactor project, which is just pathetic. And if I have a DOE spy on, that's okay, because they know I'm very negative. They spent billions and billions of dollars designing these advanced reactor concepts, working on technologies. Without building a reactor, you're just never going to get anywhere unless you start doing something. And they really have just failed because they've become too expensive and dragged on without progress. It hasn't been political issues or regulations. Regulations usually a good scapegoat people use for why we haven't built reactors. But I would say that's, it's really been a combination of factors. And it's really just they tried to take too large of a first step. You always want to make something really cool, really high performance. And that's what's fun to do on paper. And if there's anybody that should be doing that, it's universities. So and you notice universities are the only people on my list that aren't at fault. So you're lucky there. Congress is a big part of the problem, and decision makers at the top, the bureaucrats who care where the money goes instead of what's getting done. And then the labs, even Los Alamos or corporations, usually just follow the money. There's some project, oh, we want this reactor to do this, let's do it. And engineers, we're all at fault too. We usually, a lot of times we'll take, say, oh, that's cool, let's try to do that. It's really hard, but it's cool, instead of recommending pragmatic solutions to things. So why space reactors? tons of great uses, and this is pretty easy to sell, and it's never been a problem. That's why space reactors are still of interest even after 40 years of failure. It keeps coming back because there's tons of great stuff to do. I'm not going to go into that. As usual, I have a ton of slides. As you can see, 63, and I won't get them through them all in 45 or so minutes, so I'm going to go really fast. But the thing that really makes reactors great in space is on the surface of Mars and the Moon, or in deep space. But there's a lot of talk about, you know, expanding into space, and Elon Musk is without him we'd probably be lost, because he's really pushed us in that direction to get Earth to orbit transport going. But Mars is tough just because of the dust storms mostly, and the easy water is at low altitude, at high altitudes. The Moon is probably more challenging just because of the 14 days of darkness. And the storage system becomes the problem. The batteries, you know, keeping everything warm during the night, not really how many solar panels you need. And the water we want is in permanently shaded craters, which makes a reactor very, very good. This chart kind of puts everything in perspective for power in terms of electricity on the left, length on the right. You know, chemical systems are awesome for getting high power, but you know, they just, if you need to bring oxidizer with you, which you do in space, unlike Earth, it becomes a really a problem to try to get a chemical reaction going. Solar is awesome. This is an outer planets line, but you know, it's not going to get very far. Radioisotope systems have been great for getting us to explore deep space. The problem there is we've run out of Pu-238 mostly. That was all legacy weapons program stuff. And at Oak Ridge, if you guys know, they are starting to make some Pu-238, but it's not going to be enough. At most, it'll be enough for like one mission a decade. So reactors can fill kind of the deep space exploration niche, and then out to surface power and nuclear electric propulsion, and maybe eventually nuclear thermal rockets. All right. So I want to kind of put this in perspective before I really want to talk about KRUSTY the most here, but this is a chart that kind of shows in green reactors that we were successful at, that were all built like, you know, 60s and 70s, where this is power density and this is temperature. You know, we've kind of been in a range, you know, FFTF and EBR2 were pretty high power density, still pretty low temperature. KRUSTY in the 1 kilowatt is way over here, super low power density, but high temperature, 800 C. And then other space reactor projects. But the one thing I really like to point out is how difficult nuclear thermal propulsion is. And there's a lot of people out there thinking we can do this like in the near term, and I think they're wrong. I've told NASA this and DARPA this and others, but you know, this is the only nuclear thermal rocket prototype tested that we had some of the key rocket components from the Nerva rover program. And they took 19 tests to get there, and $10 billion in today dollars. And today they're trying to develop an NTR concept. They're talking about that's an order of magnitude harder, and it's incredibly hard. And over here is on the log scale. It shows how high these high power densities are. So that just kind of leads into, I love nuclear thermal propulsion. It's the coolest thing to work on. I did my PhD in nuclear thermal propulsion, and I don't blame you if you do, except it's still a long way off and may never happen. You know, I could go into all the reasons why what they did in rover Nerva was not only way simpler than anything anybody wants today, it was lower performance, and it still wasn't close to flight. And they spent $10 billion and did 19 nuclear ground tests. We'd be lucky if we could do one. So it's just really hard. I tend to think nuclear electric propulsion is the future, but I don't want people to start really jumping there to these big systems either. We can the nice thing is we can evolve to NEP, and it's, you know, there's work on the thrusters and power conversion can be independent of the reactor, and we can get there step by step. And it's truly game changing versus NTP, where you get a specific impulse of 2 improvement. Here you can get 10. So that's kind of my long-term picture. But my focus is really to try to get students, you know, grounded in reality in a lot of sense. You know, to try to push actual reactor technology more than coming up with fancy reactor designs that might be good someday. And I know that's tough, and it's hard to get money to do real things. We struggle with that right now because people always want something better. But the bar keeps getting higher every year. We don't fly a reactor or build a new reactor because the other technologies get better. Solar is getting better and better every day. It is near its peak, but it gets tougher. So this is a picture of kilopower reactors on the ground. Yeah, and just to mention safety, the one great thing about working on space reactors is typical safety is not a big deal. We start with almost no radioactivity, 1 to 10 curies. It's mostly the U-234 that's enriched with the U-235. But it's way lower than any of the current radioisotope systems we launch. Not a health risk. So all we have to worry about is that it doesn't fission before it gets to where its destination is. And we design them to stay subcritical in all launch accident conditions, whether it's falls in the ocean, there's a launch pad fire, I get surrounded with sand. Really, the only way the reactor can generate power is if the reflector is on and the B-VII rod is withdrawn. Otherwise, it won't go critical, which made us it really helped us elsewhere. That feature was great for ground safety and everything. And so when you're on the like humans around the reactor, they're far more worried about it producing power than getting a small amount of radiation dose. So because power is, if they lose power, they'll die. And so that's really reliability becomes your big issue. All right, so finally we're to a kilopower concept. And so it's incredibly simple, and that's by design. In the center here, this kind of rust-colored thing, depending on the color of your screen, that's a solid cast of HEU. We have LEU designs, as you'll see, but that was made at Y12, and it's basically the same casting process they use daily. And that's what made this whole thing possible. And what makes this design really nice is the fuel is readily available and fabricable. So there's this fuel, there's a central B-VII rod that controls the reactivity, gets pulled out the bottom. Then you're surrounded by beryllium oxide. And if you've done any work on reactors and trying to get a high worth reflector, there's nothing like beryllium. Either beryllium metal or beryllium oxide. Beryllium oxide is a little more effective. It actually, because it packs in just as much as beryllium, but includes oxide, oxygen, and oxygen's an unbelievably good fast neutron scatter, one of the best there is. So it really reflects the neutrons back. The core by itself is far from critical. And I have a slide that shows that. Then there's a bunch of shielding. Lithium hydride and tungsten. It could be any material. In fact, high Z material doesn't even really matter that much in the fast spectrum. It could actually just be stainless steel and aluminum, but it makes it a little thinner being tungsten. Then there's heat pipes that come up and attach to Stirling engines that produce electricity, and then their cold side is connected to a radiator. And the reactor we tested is this one. KRUSTY was exact prototype really of this reactor. Then there's, if we want to get 50 kilowatts out, we put in a lot more heat pipes. If we have to use LEU, you can see the HALEU, if you know that term, the 19.75 enriched. It just becomes a lot bigger. The core mass becomes huge, which is a big penalty at 1 kilowatt. It's less of a penalty at 10 kilowatts, and it starts to go away at higher powers. So the three basic things that you guys should all know this, you know, we're basically, we're making fission power in this chunk of metal, you know, and then, so the power is deposited in the fuel meat by the fission fragments, or at least 95% of it is, maybe 92% of it is, but 95%, 96% is of the total energy is in the fuel. And then it conducts to a heat pipe that's in this slot. And the heat pipe is the is a closed tube. I'm sure you've dealt with or heard about, which you boil at the evaporator end. You boil, in this case, a liquid metal. It builds up a vapor pressure. Vapor pressure drives the sodium vapor, in this case, down to the condenser where there's something cold removing heat. So it condenses. It gives all of its HFG back to the wall, and then you use a capillary force, a wicking force, to bring the fluid back. And these were actually invented in Los Alamos. The guys who invented it really envisioned it for space reactors, you know, but it's been used millions of places. You know, every laptop has a heat pipe, but it's, you know, it's a water. Every good laptop, I guess, that has enough power, and so their heat pipes are great. And then it connects to a Stirling engine, which creates electricity, just with the standard heat engine. So how did we get to Kilopower, DUF, and KRUSTY? We'd liked heat pipe reactors from when I showed up at Los Alamos. That's what I started to pursue, because they have a lot of great reasons. Things, and you'll see that in some of the test results. But in this case, we got heaters going into a heat pipe reactor, so the heaters can mimic the power deposition of the fuel, which lets you electrically test the system without having to breach any boundaries, pressure boundaries. So it's really nice. In this case, we were connected to a rather big Stirling engine that gave power to a Deep Space One ion thruster. This was a JPL. This is, you know, this is like 20 years ago. And it all worked good. We love the heat pipe reactor. Oh, this one's over here have gas heat exchangers on them to feed Brayton heat cycles. But it was always, people said, yeah, the heat pipe reactor is great. No one's ever operated one. You know, we'd say, well, it should be really simple, but it didn't, you know, it never gained traction until we did the test. So that's kind of when, in 2012, there were 3 people sitting around in our office. It was me, Pat McClure, and David Dixon. We talked about Dixon before, a UT recent PhD graduate, but probably not recent enough for any of the current students to know him. He was awesome. And so and Duff is his middle name. So actually, Duff, there's more of a Simpsons theme than a Dixon theme, but Duff worked good because it was Dixon's name. So this test, we said, you know, we haven't done anything our whole careers. We got to come up with something we can do to get NASA excited, show that we can build a reactor or do anything nuclear again. So we came up with this idea to use an existing machine at the Nevada test site and put a heat pipe in the hole in the fuel and connect it to Stirling engines. And we thought we could do it for a few hundred K, you know, which when the government is nothing. But we couldn't get any interest. And then actually the lab offered voluntary separation package, and I was fed up and I was going to leave and go be a professor at Michigan. And they finally came through and said, all right, we'll give you the 200K to do this test. And we pulled it off. So we did a lot. We showed that, yeah, we could still we use nuclear power to power a Stirling engine. It wasn't anything really impressive. We got data and benchmark it, which is nice, but that's that really is what got NASA interested enough to listen to us on the next thing. And this is Dixon. He's got it. Look, he's got his, I think that's an NC State shirt on right there. So he doesn't have his Tennessee, sorry. All right. So this is when it got good, because we said, all right, what can we do for a reasonable amount of money, which was $10 to $20 million to test a reactor. And so we took our Kilopower flight concept, developed a KRUSTY design, and we were able to sell it to NASA to get going. And what we did, we really decided, what do we want to make prototypic? And the thing we wanted to make most prototypic was the dynamics of the system, stability, load following, would a heat pipe cooled reactor work? And then we went down a list. You know, it was kind of like we had to avoid the temptation to want to make this test perfect, or would have become too expensive and we might not have pulled it off. So we made sure we ended up meeting almost everything, which is something, except for shielding and reflector temperature and to some extent reactor control. But we did a great job coming close and pulled it all off. But it was important to sit down and, instead of just saying what's the coolest, best thing we could design, it's what's the best thing we can design that can actually get built and tested. The one thing, the U-moly fuel is really good stuff. Your metal fuel was, so that was easy to choose for us because it works great. It's high density, high thermal conductivity, but we had a place we could make it. And the reason we use molybdenum, or we could have used zirconium, but moly was better for this case, is you put in that moly to prevent a phase change when you heat up and cool down. You could get thermal cycling with the phase change that could cause you issues, and the more moly you have, the more time you have to go through the potential phase change region. This is what the actual KRUSTY looked like, where the big difference you'll notice is instead of withdrawing the control rod or startup rod, I call it, you'll see we don't even need it for reactor control. It's really just to start up. Instead of doing that, we raised the reflector around the reactor. And if you guys have done any reactor kinetics, you know, the best thing since sliced bread is the point kinetics modeling, right? Because that makes it really simple to model your reactor. And luckily, or, you know, kind of by design, this reactor is a point kinetics reactor. So it's sweet. It doesn't matter where we insert reactivity, the whole thing talks to each other, because the mean free path of the neutrons is on the order, you know, mean free path of the neutrons 3 to 4 centimeters. The whole core is like from the center to the outside, it's 4 to 5 centimeters. So it really made it easy to model, easy to predict, and it didn't matter where we inserted our reactivity from a system performance standpoint. So you know, this started mostly, you know, it did start with an MCMP model, you know. So you know, you know, you can make fun of people who just think designing reactors is running you know, an MCMP or neutronics model, which is not. But at least this case, it started with it. And I had codes that did the heat transfer when I created the MCMP models, and we turned them to design drawings, you know, and there was a lot of iteration. As you'd expect in a real project, you don't just make your model and they build it. They tell you, you're gonna have to change the design so we can put a weld here or do something or get a tolerance. A lot of back and forth. And that's one thing a lot of nuclear engineers are missing, because you know, they've never built anything. And in a reactor, you know, when you're building something, there's always a lot of interplay between fabrication, material stock, availability, the whole works. And there's a lot, you need a lot of margin to handle that. So we did three steps in this development path. And this was another thing, just to make sure we had a milestone every year. First year, we had this kind of built up, mocked up a stainless steel version of the core, just to kind of show form, fit, and function. Then we did a electrically heated test with a depleted uranium core in year 2. And then year 3 was the actual nuclear test. And it all went incredibly smoothly, which was pretty remarkable. So this is the thermal prototype. So this is stainless steel version of our core. But there were 2 key things to test here. One was our core structure is these bands which we heat up, and they shrink fit and hold the heat pipes next to the fuel. It gives us the thermal bond and the mechanical bond. And if you know your heat transfer, and you're in a vacuum, it's tough to get heat transfer. We take for granted that we have air between our hand and the heater or anything here to get heat transfer between surfaces. But in the vacuum, you got to have some tight physical contact to get heat transfer between components. And so that's what this does, and it holds it. And then we got a heater. NASA Marshall made this awesome heater. This went up to 10 kilowatts. It's a graphite resistance heater, which could go into the middle of the core here, and then there were calorimeters on the heat pipes to get the heat out. We did a lot of benchmarking with the second year, the resistance heated test, which was huge, just not to work out kinks and develop where we could put instrumentation. But one of the key things to this whole process, which Pat McClure could talk about for a while, is, we had the regulators in from day one, seeing everything we did, getting confidence in what we were doing. And that was easier because the DOE was probably more receptive to the NRC, but the DOE was a regulator here. They followed basically the same stock of, rules, regulations that the NRC does. But we brought them along, gave them confidence, and eventually we used this to benchmark the codes to get regulator approval. This is putting the core together. So there are 3 pieces of this HEU. Here they are banded together. This is the flange to the vacuum chamber, so it'd all be in a vacuum. I mentioned how safe this was because of how great the beryllium oxide reflector was. You could do anything you wanted with these 3 fuel pieces and never go critical, which, unless it was surrounded by beryllium or another fission material. So it made operations easy. We could get approval to do pretty much anything because it was impossible to have a criticality accident if you didn't have the beryllium in the area. And that's, it was the same reason we designed it, so it'd be safe if it fell into the ocean or Miami Beach or any place. We did have to worry, there were a lot of safety calculations. We did have to worry if we inserted reactivity too fast, we could melt. And this is just the function of how fast that platen or lift table moved per time. So we had to make sure we couldn't lift it so fast that we would get too big of a power spike, basically get too high of a reactor period, too high of much power in that case. This is actually at the DAF, so this is getting ready for the nuclear test. This is the heater that Mark Gibson designed to heat up the rings and bring it down over the fuel. So here's the actual heat pipes with the HEU fuel in the middle, and he's sliding a heated clamp down over. This is the beryllium oxide part of it. Another NASA engineer attaching thermocouples. We wanted to get as many as we could. Below it is just shielding. We had to prevent the room from getting activated because they do a lot of sensitive work at this facility, and we couldn't activate the room to give them a high background. So it's mostly steel because that was cheap and easy. There's a couple layers of boron carbide here to reduce our neutron flux to the room as well. We did 70 zero power criticals, which were big in benchmarking the codes. So zero power critical, I know I don't have a clock, which is bad. But the way you do a zero power critical is, you set you insert your reactivity until you start to see power rise, right? And you get on your reactor period. And then based on the in-hour equation, you can figure out how supercritical you are. So you measure each one of these tests. We found how many cents supercritical we are, and we're able to benchmark the codes. And MCMP and the ENDF data was awesome. And this is the boron carbide pucks that we simulated the worth of the internal rod. So we got the worth of our control rod. We just didn't move it actively during the test because that would have required a safety rated system to move the control rod. And so instead we just did it physically by stacking up these pucks. All right, nuclear power. So this is what I was talking about. This is a 15-cent free run. So 15 cents of reactivity and supercritical. And the way you know that is you get an exponential rise in power. And in this case, our reactor period is about 45 seconds, such that we're going up a factor of E in power every 45 seconds. And that corresponds to 15 cents. And we did this every test. This was another thing we did with the regulator to get approval. We're going to start every test exactly the same way. And if it's not behaving the same way as it did before, we know we've changed something, done something, and we'll stop and figure it out. So after the power increases enough, you start to get sensible heat, but we're going from watts to kilowatts here over this time state. So it starts to heat up, and then once it heats up enough, the power starts to turn over. Oh, I'll wait till the next slide. This just shows to talk about that. This shows the fuel. There's thermocouples in here underneath these clamps, which are kind of spring loaded, again, to get in a vacuum, to get a decent reading with spring loaded against the fuel. And how they were coupled to the fuel it was a big issue when it was cold. Once everything expanded, the thermocouples were great, but when it was cold, they weren't fantastic. And this is the beryllium oxide, really nice pieces made by a company called Materion in Tucson, and that's a thermocouple taped in the middle of the BEO. So this run, we get up, and so once we start to heat up enough, then our power turns over because the reactivity feedback. And what I think is great about fast reactors, and especially this really high leakage rate reactor, is our reactivity is 100%, well, actually you'll see like 95% dominated by physical expansion. It's as simple as the fuel heats up, the atoms get physically further apart, more neutrons leak out. That's our control mechanism, not having to know all the Doppler coefficients and other things. And it really makes it easy to predict, and it's linear, basically, as I'll show you. It worked out really well. So what happens is, once it starts to heat up, our reactivity goes negative. In this case, it would have taken a long time for the temperature to get down to where we see power start to come back up. And that'll become evident in the next slide. So here's the fuel feedback. There's a ton of feedback coefficients, and several are positive, but positive coefficient doesn't matter if it's in the noise or depending on the time scale. But the fuel dominates our feedback, which made everything really easy. And so what we had to do to really understand our reactor before we operated was get a good sense of the coefficient of thermal expansion in uranium. So it wasn't cross sections or anything nuclear. Understanding our reactor control was testing the coefficient of thermal expansion, and we ended up nailing it with doing a lot of testing. At least it predicted the fuel feedback almost perfectly. The other nice thing about the U-moly is that CTE matches very well with the other materials we're using, which is what you always want in a real design. The last thing here was of the 15-cent run, which is again our first nuclear powered case, is we're just sitting there watching the fuel cool over the course of a couple hours. This really gave us what the thermal losses from the system was through our multi-layer insulation. And another thing, is it's almost impossible to predict how MLI is going to perform. We actually did a lot of tests to try to figure out what layer, how much thermal resistance 10 layers of MLI would give us, but it never really matches, because how you wrap it around your insulation, around your things, and the environment it's in, and how many thermal cycles it may have been through will change it. So this told us how much heat we were losing, which was huge for later benchmarking. Two more tests, 30-cent run. So what we did for all the rest of the tests, we started with this 15-cent run, where we got on the 15-second ramp, turned over. But then when we got back to 3 kilowatts, we started to insert more reactivity. Till this case, we inserted 60-cent run. Now, you might say, how did you know you were at 3 kilowatts? We didn't until we did the first test. There's no dial you put on your reactor to say, here's how much reactor fission power there is, right? You got to infer it based on other data. And if I go back to the 30-cent run, so whoops, wrong way. We basically, in this test, this is a neutron detector, right? This is a counter, a helium-3 detector. And so we know how many counts we had, the integral over this curve, and we know how much our fuel heated up. So we take the thermal capacitance of our fuel, specific heat times the mass. We know how much heat was put in based on how many counts we had. And then we get our powers actually our amperage from our detector times 5.6 times 10 to the 8th. So that was an important thing to do early on. So finally, the 60-cent run, we keep inserting reactivity, and this is an operator just moving the table up slightly whenever the power went below 3 kilowatts. This was huge because this was the test. As I mentioned before, the regulator, whether it's the NRC or the DOE, they don't know your reactor as well as you do, obviously. And they don't really have the ability to model it unless you're doing some small offshoot of an LWR. And so we convinced the regulator, actually just got them to trust us by taking several steps along the way. Here's what's going to happen next, and it happened. And this was the final negotiation. If we could predict the temperature within plus or minus 10%, the peak temperature we hit on this test, we had approval, we'd get approval to go to the next test. If we missed this, we were back kind of to square one on a safety basis. And so the morning of the test, I emailed out to everybody, predicted 447 C, and that peak was actually 446, which was insane. That was luck, and there's no question, because I thought I had at least plus or minus 10 degrees on my prediction. Pat McClure done a good job negotiating because he got 10% margin in Kelvin instead of Celsius, because that gives you 80% more margin for 10%. So we had a lot of margin, but we nailed it. And I haven't seen what time it is, but I bet it's probably not good. I'm just going to keep going.
Hey, David, you have another 10 minutes or so.
Oh, good. I'm not doing too bad. I'm rushing,
no,
but
you're doing great.
I can't tell how fast I'm rushing. So this has really demonstrated the key point of this simple reactor, and so it shows what we call the thermostat. What you're doing. The one thing that you have to get in your mind as a reactor engineer is that your control system controls temperature, not power, to the first order. I mean, obviously, it affects reactivity, but what it's really doing is setting the temperature the reactor wants to be at. And so when we set our reactor at 60 cents subcritical, if you look at our feedback coefficient, the fuel's going to want to get to 400 C to counteract that 60 cents. And that's exactly what we did. When we resisted the 60 cents, we made the reactor want to be, to exist at 400 C, because that's the only place where its feedback would balance what we'd insert. And so when we put in the 60 cents, temperature goes up. We hit that 447. And then once we're above 400, though, the temperature's too high. So remember, more neutrons are leaking out because we've expanded. So too many neutrons are leaking out. That makes reactivity negative and power go down. So that's what happens here. Power goes down and down and down, way down, to less than 10 watts because we stayed up above 400 for a while. This is really an interesting academic study here, is that where it bottoms out is really based on your source. This is another thing that might blow people's minds, but you're never critical in a reactor because there's always some neutron source. You're always multiplying a source. You're just multiplying a source by, 0.99999, by some number so that you're staying critical. And where we bottomed here was our neutron, we were multiplying our source, was actually photoneutrons. Our decay gammas from the fuel were hitting the beryllium, creating photoneutrons, because otherwise we would have bottomed out where our actual neutron source was, which was about another order of magnitude lower. So this was kind of cool to figure out why we bottomed out right here. But then as we're cooling down, once we get back to our thermostat, all of a sudden our reactivity is 0 and positive. So power starts to come up, and power comes up until we drop below 400. And then the reactivity starts to change our slope of power and back and forth. And we get these oscillations to our stable point. And what is our stable point? It's the 400C thermostat. Is how much power do we lose at 400C? And that comes back to that MLI issue. How much power is being lost from the reactor? It's 100 watts. And so these are really slow oscillations. It's kind of like a pendulum. If a pendulum, how fast it swings is based, gravity is kind of the driving force here. Heat removal is for how long it takes to cool down due to power draw. So this showed the basic physics we wanted to show and set us up for the final run. There was some other academic stuff. Was we failed our turbo pump during this test, which was bad, but we were lucky that our roughing pumps kept the pressure low enough throughout the rest of the testing to be decent. We're actually pretty close to the pressure on Mars, actually, but still an order of magnitude lower, so it was okay. So this is the power conversion system. There were only 2 real Stirling engines, one here and here, because we were just taking what we get off the shelf. Another interesting part was we designed these simulators where here we float nitrogen through a copper heat exchanger that looked exactly like the same as what's in the Stirling engine. A Stirling engine has helium gas in it that's pushed back and forth by piston over a heat exchanger to get the heat out. Here we just flowed nitrogen gas over the same kind of copper heat acceptor, and it worked great nominally. It worked horribly when we simulated failed heat pipes. Well, not horribly, but it just didn't do everything we would have totally wanted. But that was, again, just trying to make sure we got something done instead of doing everything perfect. Here's some thermocouples. We had a lot of thermocouples up on here. And this just shows the extent of all of our thermocouples. And you can never, as a designer, you never get enough. And I was always begging for more, but we were able to get in this much capability. So we had over 100 thermocouples and got some pretty good data. Not as much as I'd like, but it was good. There's some cool academic stuff on peaking factors, which are important in your design. But this shows there was clamps. So where the fuel sees the reflector without a clamp, it gets a little more power. But this is all kind of in the noise. Your distribution changes as you move the platen and all that. But more academic. Same with there is a peak, thermal peak of neutrons coming back from the reflector that have been moderated a little by the beryllium. Again, more of academic interest, but you have to make sure you can handle whatever peaking you've got. Probably more important is just where all the power goes. So you have to account for all the power in the shield, the reflector, everywhere. And your shield's job is to absorb energy, right? That's what a rad is energy. So if your shield's doing its job, it's gonna absorb energy. So we're getting to the final test. This is the control room. Me and Mark Gibson at the controls for KRUSTY, which was controlling all the power conversion and flow. And then the control for the reactor is really just this joystick. They can move the table up and down, and that's it. And for most of the tests, because our point was to show you didn't have to control this reactor when it operated, they just had to sit there. So their job was pretty boring, except for a couple of the transients where we let them move the control. That's Pat back there. He's checking Oklahoma Sooner football news, I think, because he's a huge Sooner fan. This is the system in the vacuum chamber. So the core's here. This is a vacuum can around it, and all of the power conversions up here, and it's slid into the stainless steel radial shield. And this is when it's installed on test day. Here's our beryllium getting ready to lift to make it go critical. The startup was fascinating, a lot of interesting stuff going on. Here's our, remember we always started with this, and the DOE guy was there and the regulator was there. You know, we had to be following this path or we'd shut down. And then we just inserted reactivity this time until we got up to 800 C for our set point. And there was one interesting point here and here. Heat pipe reactors, the problem with the heat pipe is when it's not at a high enough temperature to overcome its heat transport limits, you know, it has some issues. And what happened here, we started up really fast because we had a limited amount of time to run. We negotiated 28 hours of running. Remember I talked about we couldn't activate the facility. And so we wanted to start as fast as we could to get as many transients as we could. And in this case, the heat pipes, this is the top of the reactor. So the sodium's coming down from the heat pipe cooling the top of the reactor, but it's not getting to the bottom of the reactor. So we're operating our heat pipes faster than they can transfer heat. In this case, it's a flooding limit where the sodium was only making it down as far as here, boiling and going back to the top. But as the heat pipes heated up, they finally got hot enough, and I'll show on the next slide, that they operated below their limits. And actually for a while, they were taking more than 3 kilowatts. And so the core followed and produced more power for that. But this was actually a success because we showed where the limits were of the heat pipes, how fast was a good time to start up. It got a little dicey though, because the DOE, guy was sitting there hitting ready the scram button because I said we wouldn't exceed 800 during startup. It was going up, but then it came down. And then we were okay to go over 800 after that. This shows the heat pipes. There's 3 limits. A sonic limit is what you'd expect. The vapor can only travel at the speed of sound. So there's a limit depending on the vapor pressure, how fast heat can travel. Then there's a viscous limit really for how the viscosity of the fluid, how it can move. And then there was a flooding limit. And during startup, we were on our limits. By definition, you're always going to start up on your limits. But then once we got the heat pipes hot enough, they performed unbelievably well, better than our wildest dreams, really. It really was like you just modeled an infant conductor and the core and the power conversion talk to each other. There's a lot of cool stuff.
David, we just have a couple minutes left.
All right.
And then we have questions.
So I'm going to go to really the coup de grace was this shows the load following data. So, I mean, this is really cool because it's the first new reactor data in 40 years, right? So it's cool enough from a new kind of reactor, but it shows how great it is from a control perspective. So we're at our core thermostat. The fuel wants to be at 800 degrees, right? So we're cruising along at what would be called our nominal power. We all of a sudden reduce the stroke on our Stirling engines, more power out. So less power is being removed. So what happens? The fuel temperature goes up. Fuel temperature gets above our thermostat temperature, power drops, and then we do the same oscillation. In this case, the oscillations are about 15 minutes. So then we go back to nominal. The reactor just puts out nominal power. We go up to 4 kilowatts in this case reactor. So here, our reactor is just responding to the control system. We're not controlling the reactor at all. It controls itself and self-regulates and put out whatever power you want. And the key to that is you stop removing power altogether. It goes down to match the power of the passive loss, whether it's that 100 watts or so. So you don't need to control it even for a total loss of heat removal. So it's totally okay on its own without any control. We love the heat pipe reactor because of you avoid the single fault tolerance. And so we simulated a failed heat pipe or a failed Stirling engine. And it performed exactly as expected. But these are the model, we weren't measuring temperature inside, we were just measuring temperature outside the core. But these thermal couples responded exactly as we predicted they would. first failure. So show we can accommodate failures. This is where we actually move the platen, the reactivity, to show how much temperature changed with a movement and reactivity, and those were very smooth transients. So we crammed in as many transients as I want, just kind of like how I'm trying to cram in as many slides as I can. And another great thing about this with how we dealt with the regulator, we had an envelope we could operate, but we didn't have to stick to a test plan. And I actually came up with this test plan the night before the test, because we wouldn't know how long it took to settle between transients until we did these early tests for sure. And that 60-second run kind of told us how long we're going to settle. So we did all these transients and were able to come up with the test plan, the morning of the test. We did make electricity. Stirling engines worked great. This slide just kind of shows our electricity production. Then I was just going to talk about how great it is, the point kinetics. We don't need to do any more nuclear powered testing for any system like this, because they're so simple and we show we can model it and predict it. This slide was just to show how crazy, how many things will show up when you're designing a reactor that you didn't think of, or you did think of, that will control your design. It just means put in a lot of margin. Don't oversell your concept by designing it on paper to limits. We have a lot of, I think I have over 63 shoot, but a lot of ways we can use KRUSTY exactly in a space or a surface configuration. Getting to high powers, the key is the physics. We can just always rely on the last previous systems in our model to predict what's going to happen, because nuclear testing is so hard and difficult. We'll see how INL and others do if they actually make any of these current reactor projects succeed. The evolution to high powers is switching fuel type. U-moly fuel swells a lot. So eventually we're going to go to UO2 or UN at higher powers. And we're going to go probably to a Brayton power conversion system. So we'll evolve technologies, but kind of keep the physics the same. The great thing about the reactors is how much more power we get per kilogram as power goes up. Versus solar, it's a total slam dunk on Mars because of the mass of the extra mass you need for dust storms and for storage overnight. And this is the last slide, just that really it was pretty amazing we got this done for less than 20 million, and it was a credit to everyone involved that we were able to pull off an actual reactor test. The keys to success: integrated simplicity, not just the simplest design, but the simplest path, right? But design, development, fabrication, safety, and testing. 100% best is the enemy of good enough will kill anybody. You got to avoid the temptation to make things perfect and feel good about yourself for getting an elegant solution to a problem, because you just need to make sure it can still be built and be useful. A small, tightly integrated team is totally required. These big behemoth projects are too disconnected. These hundreds of $1 million projects. And management left the decisions to the design team. NSA and NASA worked great. And integrating the regulators early was huge. So that, I hope, was that was the last slide. I got a lot of cool backup, but I guess I'm ready for questions if we have any time for that.
Hey, thanks a lot, David. I see there's a question here in chat. It's from Dr. Upadhyaya. It says, the oscillatory nature of fission power seems to have a second order damped dynamics. The heat pipe technology used in the Westinghouse ENVISION microreactor. Oh, the heat pipe technology is used in the Westinghouse ENVISION microreactor. Great talk. So do you have any comments? I guess you have the oscillatory, the second order damped dynamics, because you're making too much heat, you're not making enough heat, and it just kind of settles you into steady state, right?
Yeah. And eventually literally started as our concept. Westinghouse bought the license from the lab. Yeah, the whole microreactor project, I'm kind of going, if you look at the history of microreactors, we proposed a microreactor to DARPA 10 years ago based on this technology. And then we briefed the Defense Science Board a lot on what we called Megapower, which is our megawatt like Mars surface reactor, and got the Defense Science Board totally on board, and the government program started. And then, but then Westinghouse wanted to use our concept. It's evolved Da Vinci. It's a little bit different, but it's the same. But unfortunately, in my opinion, I think they've messed up specifying TRISO fuel. The safety benefit is minuscule based on all the problems you're going to have by a low density fuel. So,
yeah.
But from the heat pipe perspective, yeah, it's going to work the same, and really, I think, be a big benefit. The heat pipe, it's just hard to build. I mean, that's the problem with the heat pipe reactor, and hopefully 3D printing will help with that.
You have a few more questions here. So Karen Hook says, what was the mass of the uranium in the 1 kilowatt design that you tested?
Yeah, good question. It was 28 kilograms, which is, it's below the threshold to make a really good, easy weapon. But you know, safeguards is the reason that pushes us to lower, to potentially use HALEU. But the good thing about this, I mean, it's still, the laws exist to use HEU, and we did. You know, we made HEU there in Oak Ridge at Y12, shipped it across the country, used it, and it worked great. We have security precautions. I'm kind of taking a tangent. We have all the things into place to keep it safe, and then once it's in space, it's okay. But yeah, it was 28 kilograms of HEU.
Okay. Christian Xavier says, if you're exploring uranium oxide or nitride fuel for the future, is there a possibility that KRUSTY could be modified into a small scale nuclear thermal rocket?
We did put in for a demo. It would be very small scale and not very useful. But with NASA, we developed them a demonstration nuclear thermal rocket that only had a few pounds of thrust and got like, you know, 500 seconds of ISP based on this to demonstrate the technology. But it's not going to get, it's not going to be, it's not going to expand. I think when we go to nuclear thermal rockets, my favorite is the thermat fuel by far, or just go back to what they did at Rover and Nerva. But everything, again, the use of the moderated systems that are driven by the desire to use TRISO, in my opinion, the problem. If you're going to moderate a reactor, you're going to wait until you start it up and try to operate it to know if you have something that works. And that's the biggest risk you're taking. It's not whether you're going to hold the hydrogen, which is an issue, or whether you know the cross sections well enough to go critical. The thing that scares me most about a moderated reactor is we don't have the ability to test and feel out and figure out how to operate, and if they'll operate stably, a moderated reactor.
Here's a question from one of our sophomores, Nick Damon. He says, are nuclear thermal power rockets able to be operated in the Earth's atmosphere, or do you need an initial stage chemical device?
Yeah, initial stage chemical for sure. And we've gotten so good at it that there's no reason for us really to do anything else. Initially, you know, they talked nuclear airplane and launching nuclear thermal rockets from the Earth, but those days are past. Even if you could get it approved from a safety perspective, which you probably couldn't, we'd never make one as efficient as like the Falcon Heavy. Really, it cost effective is the
yeah.
So,
yeah.
So
okay, here's probably our last question from one of our research faculty. Well, actually, one just jumped in. So Michael Leisenfeld says, in your opinion, will Elon Musk recognize and publicly assert the necessity of fission for space exploration?
Man, that's an awesome question. The reason I say that is because it's like, publicly is the key. which is weird for Elon. I've met with Elon 3 times. He's the greatest thing ever. I mean, anybody that has any negative to say about him, I shake my head because he's amazing. And he does recognize he's going to need fission, but he also does own a solar power company, so he wants solar to work as much as it can.
Right.
But all of his engineers tell him and us, you show him that the solar route is, let me show you, not only big, but heavy. So this is kind of the evolution, say, of a Mars base. So this is 300 people on Mars. It was 410 metric tons for the solar versus 780 for the reactor, huge. And you just look at the size of the solar panel farms versus, these are like our big micro reactors to power the city. So he recognizes that he does say he doesn't want to enter the nuclear foray. He wants to focus on transportation right now, and he knows as soon as he brings up nuclear, he'll bring in some enemies, which we all know. But he has said it. If you look at it, he said it a couple of times. And there was a Twitter feed where somebody said he's recognized it, but I haven't seen a quote from him. So I don't think there's a public quote yet, but that's a great question.
Okay. Well, Dave, thank you very much. We're out of time. Exciting talk. It's great to see someone go out and actually do something, have a new reactor, operate it, take data on it, have plans for the future, and just fabulous talk, and good luck in your future too. So what is the next step? What is the next step?
You don't want to know. Well, because DOE, it's NASA's given focus back to DOE NE, the same program, that has messed everything up. We went around NE to do this, and they hate us for it. And they love Idaho, as you probably know. And they want everything to go through Idaho, such that there's official NASA program, DOE program, to put in an RFP to maybe build a space reactor. But over the last 3 years, nothing's gotten done. So me and Pat McClure and a few others have formed a company. We're Nuclear Power Incorporated. You can go to spacenukes.com, and see. And we're now working to try to do this privately. Maybe get Elon interested in funding us, or finding something. So that's a good question, because I could tell you all the negatives about the government path that are just.
Yeah. Well, this is being recorded, so we probably don't want to have it there forever.
Well, they've heard me say it a million times. But you don't want to. Yeah, you don't want to be associated with me, because the DOE.
I'll be blackballed.
Yeah, so sorry.
Okay. Hey, well, you have a super day. Great luck with your entrepreneurial spirit, and thanks so much. Bye-bye.